So one of the most commonly used fairness definition is demographic parity. So in a binary classification case, it means that you want to match the positive prediction rates of sensitive subgroups. So here A is a sensitive attribute. So in short, you want the empirical prediction y hat to be independent of the sensitive attribute A. Now, for example, if gender is a sensitive attribute, and if the yellow circles mean positive predictions and the blue ones means the negative predictions, then here you have demographic parity satisfied because the ratios are the same across the two subgroups. But oftentimes our models does not produce this binary output directly, but rather produces a continuous output. Let's call it the model belief variable. So here SA stands for the model belief variable that corresponds to the subgroup A. And we usually have a decision threshold, which is tau. So if the model output is above tau, then we give it a positive prediction. Otherwise, you have a negative prediction. And this is dependent on the threshold tau. Now, a stronger version of this is decision threshold invariant, because sometimes the user defines on the threshold, or you don't really know the threshold ahead of time. And here we just we would like the distributions of model output to match across sensitive subgroups. So instead of y hat being independent of A, the stronger version is to have the model output S to be independent of A. So a bit of notation, PSA stands for the probability distribution for the belief variable SA. So like continuing with the previous example where you have the male and the female subgroup, now if you match these two curves exactly, demographic parity is always satisfied no matter what tau you choose. So then the question is, how do we achieve SDP given a model? So there are many previous works trying to align, like make the sensitive attributes independent of your features in the input space. In particular, one of the works that, two of the works that were closest to this work applies optimal transport in the input space X, so that you produce features X prime that are independent of A. However, here we ask a more difficult question, which is if given a trained model, how do we achieve this result, SDP, but while we want to incur minimal changes to that model? So the advantage of this is also that we operate in the output space instead of the input space. So we reduce that dimensionality to 1, which is very convenient in computing Wasserstein distances. So we define this, basically we define this as fair as the model output of the fair model that after post-processing, we obtain the model that satisfies SDP. And to measure these changes to the original model, we look at this quantity expected model prediction changes that we assume that the tau distributes uniformly over your output space omega. And commonly this is just the interval from 0 to 1. And you want to minimize the expected probability that your fair model, which was the model that you produce, the difference between your original model and your fair model is when these two empirical predictions are not equal. So in other words, you can also write it in terms of the model belief variable, and it means that your tau is in between S and S fair. So your S and S fair lies on two sides of tau, so when you cut by tau, Y prime changes flips from 0 to 1 or 1 to 0. And this is the changes that we're measuring from the baseline model or the original model. Now we want to minimize these total prediction changes across subgroups, assuming that the male subgroup and the female subgroup are disjoint subgroups. So if you have multiple attributes, then you would want to consider the cross subgroups like black female, white female, black male, white male, for example. So how do we do this? A bit of background on optimal transport. So a valid transportation map is the one that preserves measures. So here from omega 1 to omega 2 while preserving the measures of the two spaces. And optimal transport map is the transport map that minimizes the total transportation cost. This is written in the original Monge formulation. And in particular, the transportation cost is a function from the omega 1 times omega 2 to the to R. And Wasserstein 1 cost is just the L1 norm of x minus Tx. So here we found some very interesting relationships between the Wasserstein distance and our objectives, as well as the deviation between two distributions. It's actually as well as the Wasserstein distance measures between two distributions measures their deviation from SDP. This is very important for measuring unfairness or how far you are from SDP, and we're going to come back to this one later. So now focus on the equivalence between 1 and 3. So the Wasserstein distance is also actually measuring our objective, which is the average model prediction changes. So now we can write out our objective, which is we want to transport the subgroup distributions to a common target distribution such that we minimize the model prediction changes expressed by this formula here. And then you can derive it and use proposition 1. Finally, you arrive at this conclusion, which is that the target distribution that you should match all subgroup distributions to in this case is the Wasserstein barycenter by the very definition. And this is basically the definition of it, where P alpha is the ratio of that group. And the Wasserstein barycenter basically stands for all weights lambda. And so computationally, this is a very simple method to use in practice. And what it does is the following. So you have 3 sensitive subgroups, group 1, group 2, and group 3, that have different distributions of model output. Now you can compute the barycenter of these 3 distributions. You arrive at a target distribution, PS bar. In the 1D case, very conveniently, the Wasserstein distance also can be computed as the integral of the differences of the inverse CDFs between your sensitive subgroup and your barycenter distribution. And so what this is saying is that if I want to minimize the Wasserstein distance between my subgroup and the target distribution, I want this integral to be 0. And in particular, I want the inverse CDFs to match from each subgroup to the target barycenter distribution, which means that I want to match all quantiles. Okay, so here I give three quantile examples. So I just pick randomly, like, okay, 10%, 50%, 90%. So to illustrate computationally how this is done, the more quantiles you match, the closer you're approximating the optimal solution. So for each of the quantile bins, now you can compute the average score according to your target distribution, right? So S1, S2, S3, and S4 stands for the average scores in each of the quantile bin according to the target distribution. And now you just map these scores back to the sensitive subgroups. And at test time, you look at the quantile bin that this particular data point's prediction fall into, and you read off the corresponding prediction according to the target distribution quantile. And one comment on this is empirically, as you will see later on in the experiment results, we didn't find a big difference between using the barycenter versus a full data set. And if you use a full data set, this is like less than 10 lines of code, and it's very, very simple to implement. So, okay, this is achieving full fairness, but sometimes we don't want that because it's too strong, and instead we would like to know the Pareto frontier between accuracy and fairness. And here, like, fairness usually involves we want to match some kind of input, output, or latent distributions across subgroups. And accuracy can be generalized to just some objective function you would like to optimize, like prediction, you want to minimize prediction errors or maximum likelihood or MAP, like whatever is your objective function. But in this case, we basically want to now find the set of solutions that optimally trade off the deviation from SDP, so unfairness, with the amount of model prediction changes. So first, in order to trade off these two, we have to define a metric that measures the deviation from SDP. And we propose this measure SPDD, which is just a pairwise demographic disparity that computes the sum of all the pairs of differences of the expected differences in positive prediction rates across all pairs of subgroups. And it's a valid measure because when it's 0, if and only if the two distributions exactly match. Now this is difficult to analytically work with, so we look at the tightest upper bound on this metric, and that gives us conveniently a sum of WOS1 distances from the subgroup distribution to the barycenter distribution. And this is basically derived from the proposition 1, but the equivalence between the WOS1 distance and the deviation from SDP. So now the question becomes, in the WOS1 metric space, how do we transport the original distribution PSA to a point denoted as P star SA, such that it optimally trade off the WOS1 distance between PSA, so the original point, and the target distribution. So that's one quantity for trading off. The other quantity is the WOS1 distance between this distribution and the target barycenter distribution. So the WOS1 distance between these two measures how unfair your model is. The WOS1 distance between these two measures how much manipulation you have done to your model. And so if you think about this, so for any fairness bound, unfairness bound like a lambda or here, it's because we have to derive it by considering each subgroups separately, so it's lambda prime minus gamma, but like the technical details you can check in the paper. So it boils down to find P star SA such that you go from PSA to along the shortest path to reach the circle in the WOS1 distance. And since WOS1 is not geodesic space, it's hard to analytically compute this, unlike, for example, WOS2 space. We propose that you use a gradient descent method to try to trace out this shortest path. So the loss function here is simply your binary model classification loss. Here we use logistic, plus a penalty loss that's a sum of the WOS1 distances from your subgroups to the barycenter, but empirical distributions. And even though post-processing have the advantage that you do not have to know the model may not be accessible to you, but you can directly change the score by putting a wrapper on top of that model. Here you have the advantage that the model is more organically changing instead of like just changing the output scores, and you don't know like exactly what you have done to the model. But also it offers you this optimal trade-off between fairness and model prediction, model manipulation. An additional advantage it has is sometimes you don't have sensitive attributes at test time, and in these cases you can still use the penalty method because you only need the group identity to compute the group empirical distributions P hat A. And you don't need that as part of your features. So at test time, you can just use the features without the sensitive attributes. And we'll see in experiment results, it generalizes pretty well. So these are 4 subgroups, the adult data set. And before we enforce this SDP onto the model, you can see that the subgroup distributions deviates from the barycenter distribution, and they are different from each other. But then after training, they all match up. So since we're using a logistic regression model, there's not really any hyperparameter tuning. So the way that we compare the results is that we have certain accuracy metrics and certain fairness metrics. So SPDD is the metric that measures deviation from so the difference in positive prediction rates compared to the full data set, and dash 0.5 are the ones that you compute the differences, but at the threshold 0.5, and you pick the hyperparameters that gives you the most fair results, and then you compare the accuracy results. So the baselines that we use on constraint is just the baseline logistic regression model. There's a hard post-processing method, and we would do a shift on the score such that the selection threshold is always at 0.5 in order to compare the metrics. Constraint optimization is just a Lagrange multiplier method on the fairness constraint that is the difference of the positive prediction rates. And advanced version of that is just, instead of using one single threshold, we use multiple thresholds for decision. And the following four methods are our methods. So the penalty method is the one I described. The penalty DB is the one where you don't use sensitive attributes at test time. Post-processing method is quantile matching. And post-processing PS hat is the one that we use a full data set instead of the optimal barrier center. And this one is the one that's super easy to implement in practice. And the empirical results do not vary too much between them. We obtain the best fairness metrics and without sacrificing too much on accuracy. So this is on adult, German, and then bank and community and crime data sets. So to sum up, the general approach that we used is from some problem objective F, we derived the cost function for optimal transport, this CXTX. And then we use this the corresponding optimal transport method with the derived cost function, and we use that to match distributions of interest so that you match the distributions of interest while either minimizing or optimizing the objective function that you care about. Yeah, thank you.